Hello, my name is Robert Strandh, and welcome to this part 2 of the series of presentations that I call Creating a Common Lisp Implementation. Just a reminder what topics are covered in this presentation series. We're going to cover the choice of the implementation language, and they're basically only going to be two choices, namely C and Common Lisp. And we are going to cover the implementation strategies for the Evaluator. I'll talk a little bit more about that later. And the division of code written in Common Lisp and code written in the implementation language. The topics that are not covered in this presentation are the following. I'm not going to talk about the details of how a Common Lisp compiler works. If there is demand, I can create such a series of presentations. I'm not going to cover different strategies for memory management. And while we're going to talk about how an abstract machine might work, I'm not going to enter into the details about it. And finally, we're going to talk about generation of native code, but I'm not going to discuss the details of how a real processor works. So just a reminder of strategy 1 that was the main topic of the first part of the presentation. We have a core written in some existing language, and the language that I chose was C. And then we have additional modules written in Common Lisp that are added to the core. And there was a question during the streaming of part 1, namely why you choose C rather than C++. And the answer is that it doesn't matter. The purpose of this strategy was to illustrate that there are complications, and those complications depend on the fact that there is an imposed order between the additional modules in Common Lisp that are loaded into the system. And that imposed order makes it necessary to write more code in the language of the core just to break circular dependencies. And those dependencies also makes the Common Lisp code of the additional modules look unnatural, because we're forced to use a subset of Common Lisp defined by the modules that are already loaded. So in fact, the situation that we have is that we have an inner core and we have an extended core. The inner core contains all that we had hoped to have to write in the implementation language, namely object allocation, memory management, accessors for built-in object types, basic arithmetic. And the extended core contains functions that have to be placed here in order to break these circular dependencies that we discussed in part 1. And it also contains temporary or permanent functions required for bootstrapping. In particular, read and eval are necessary so that we can load additional Common Lisp code into the system. So we have the following picture where we have this inner core and the extended core that we would really prefer not to be there, and then Common Lisp code that will call functionality in the core. So just a correction, I might have hinted that the core contains the basic functions of the Common Lisp standard, but in fact that's not quite true, because the lowest level functions in the Common Lisp standard are not as low as they can be. And here's an example of the function car. In Common Lisp, the function car, if it is given a cons object, it returns the contents of the car slot of the cons cell. And if it's given nil, then it returns nil. And if it's given neither, then it signals an error. So we can in fact write the car function in Common Lisp this way. using some function that we invent, namely, say, core conscar, which assumes that it's given a cons cell. So this way, the conscar function is part of the inner core, whereas the car function is not part of the core at all. It's part of the additional Common Lisp modules. So the main topic of this part 2 is the evaluator. And recall that we have the following choices: a direct interpreter, compiler generating bytecodes plus a bytecode interpreter, and a compiler generating native code. And we already said that we're not going to talk about the first possibilities. The first possibility, a direct interpreter. So the current choice for this part 2 is option 2, namely a compiler generating bytecodes plus a bytecode interpreter. So before we enter into the details of how the bytecode interpreter might work, I need to remind you of the execution environment of Common Lisp code. So first of all, we have a call stack. It's divided into stack frames. Each frame belongs to the current function being executed. And these stack frames are linked by something called the base pointer. The terminology varies. Sometimes it's called the frame pointer. And there's also a stack pointer. So the space between the base pointer and the stack pointer is the stack frame that belongs to the current function invocation. So the way this stack evolves when functions are called and functions return can be illustrated as follows. We can start with a some function at the bottom here, and if it wants to call some callee, it will start by pushing some arguments for the callee on the stack, and then it will establish an initial stack frame for the callee and call the first instruction of the callee. So now the callee will say we'll need to allocate space for its lexical variables, and so it extends its own stack frame with these lexical variables. And then if this function wants to call some other function, it passes some arguments, links up the stack frame of the callee, calls the first instruction, and then when the callee executes, it will extend the stack frame as follows. And so this goes on until we reach the last function in the call chain. And when this function needs to return, what it does, it destroys its own stack frame and reestablishes the stack frame of its caller and returns to the place where it was called from. So it will delete its stack frame and so forth. Now the call stack is not all there is to it. There is also something that we call the dynamic environment. You can think of the dynamic environment as a linked list of dynamic environment entries, and they parallel the call stack in some ways, but it's not the same thing. In fact, there could be several stack frames sharing the same dynamic environment, as is illustrated here, and there can also be several dynamic environment entries for a single stack frame. So each of these entries contains some information. It could be, for instance, a block name, a tag body tag, a catch tag. It could be an unbind protect entry, a condition handler, a restart, or a binding of a special variable. And finally, we have something called the static environment. It's the property of a function object. So we can think of a function object as containing an entry point, which is the address of the first instruction of the function, and as second slot called the static environment, which contains things like closed over variables and perhaps complicated constants. And the entry point can be shared between several functions. So if we look at this example here, we have the function foo. If it's called, it will return an anonymous function defined by this lambda here, and it closes over the variable x. So if we execute this expression here, list foo1, foo2, what we end up with is a situation sort of like this, where we have the list is up here. It contains two function objects. Each function object points to the code for the anonymous function, and they share the same code, but the static environment is different. The static environment of the first function contains 1, and the static environment of the second function contains 2. So I think that's all we need in order to define the bytecode interpreter in terms of what I'm going to call an abstract machine. I mentioned the arguments that are passed from a function to its callee, but there are also these implicit arguments that we need to take into account, which is the return address. That is the instruction to which to return when a function invocation terminates, and the static environment that I mentioned, and the dynamic environment that I mentioned. So we might end up with an abstract machine that looks somewhat like this. And I should mention that there's plenty of variation regarding how one can design such an abstract machine. And this is just one example. So just keep in mind that there could be variation here. And so if we look at the current stack frame of the current invocation of some function, then we have these implicit arguments here. We have the explicit arguments there, and then the additional lexical variables that I mentioned that the current function must create. And here's the base pointer and the stack pointer, and I added an argument pointer to simplify argument passing. Again, there's great variation possible here. This is a chunk of memory that contains the instruction stream. This, of course, is the same memory as the stack, but they're in different parts of the memory, so I show them separately. So there's a program counter that points to the next instruction to be executed, and instructions might contain arguments in the form of addresses of lexical variables or constants or something like that. And finally, there's this chunk of memory here that contains return values. Recall that the Common Lisp standard allows for a maximum value for the number of return values from a function. So we can just allocate a piece of memory and stick them there. So the instructions of the machine will then correspond to the functionality of the inner core. Namely, there would be instructions for allocating instances of built-in types. There would be instructions for predicates of those types. So there'd be an instruction that says, is this a const p, or is this a symbol p, or something like that. There'll be instructions that correspond to slot accessors for those types. So there'll be an instruction for symbol value or a symbol function or something like that. And there'll be instructions for fixed num and floating point arithmetic. So normally these instructions will work between lexical variables. So for instance, an instruction for adding two variables will take one lexical variable and another lexical variable, add them together, and store the result in a third lexical variable. So let me just illustrate this abstract machine with a somewhat complicated instruction, which would be a function call. So the way it could look is we have the current stack frame here, and we have a bunch of lexical variables. The program counter points to a call instruction, and the call instruction is followed by the address of a lexical variable that contains a function object, and that's illustrated here. And it will contain addresses of lexical variables that we are going to pass as arguments to the callee. And those are also going to be located here among the lexical variables. So the first thing we do is we link up our own stack frame by storing our base pointer in the stack frame of the callee. And next we push the return address. The return address is the address of the instruction to be executed when the call returns. We push the static environment. The static environment is part of the function that we're going to call. Then we push the dynamic environment. The dynamic environment is stored in some kind of lexical variable in here. We push the first argument. It's the value of a lexical variable. Same thing for the second argument. And now we link up the stack frame of the callee. That is, we create the initial stack frame of the callee, which is linked to our own stack frame. But now basically the current stack frame is that of the callee. And now all we need to do is to change the program counter so that it points to the first instruction of the callee. So that concludes my description of the abstract machine that is part of this first strategy. And now let's talk a little bit more about the complications that we hinted about in part 1. So the example we had in part 1 was that the mapcar function needs the do macro in order to be compiled. And the do macro function needs the mapcar function when it's executed. And so let's formalize this idea a little bit. We have execution dependencies that I illustrate with a black arrow. And so the green circle here is a macro, and the black circle is a function. So this black arrow means that the execution of A might invoke B. And by executing a macro, I mean executing the macro function. And that's typically done by the compiler at compile time. So there are two possibilities. We can either have a macro that when it executes needs to call a function, or we can have a function that when it executes needs to call another function. So for example, we might have a definition of the function catter that will invoke both car and cooter, and we get this kind of dependency. For the case when the execution of a macro depends on, or might invoke some other functions, I chose a simplified version of the case macro. As you can see here, when the macro function here is invoked, we need to call gensim, we're going to call mapcar, we're going to call first, and we're going to call rest. So we get this kind of dependency. Now the more vicious kind of dependency is a compile time dependency, and I illustrate that with a red arrow. So a red arrow means the compilation of this object might invoke that object. So we have four cases here. The compilation of a macro might need to invoke a function. Compilation of a macro might need to invoke another macro, and the compilation of a function might need to invoke another function, and the compilation of a function might need to invoke a macro. So let's just see some examples of that. Well, here's an example of how we could write the prog macro, for instance. As you can see, when we compile the prog macro, we must expand the macro multiple value bind. So we have a compile time dependency because the multiple value bind macro must then exist in order for us to be able to compile the prog macro. And here's the dependency from part 1, where compiling the mapcar function requires the macro function of the do macro to be invoked. So it must exist. So we have this compilation of the mapcar function requires the invocation of the do macro function. So if we have circular dependencies, if all the arrows are black and in some kind of circular dependency, we have no problem. These objects here can be compiled independently, and then we just call the first object in the chain, and everything will work because there is no compile time dependency. The vicious circular dependency is this one. If there is at least one red arrow in a circular dependency, we must break it somehow, because what this means that if this object here, in order for this object to be compiled, we need to, in order for this object to be compiled means it doesn't quite exist yet. We need to invoke this object, and then this object might invoke that object, which might invoke this object, which might invoke the object that doesn't exist yet. So this kind of dependency must be dealt with. So if we take the example from part 1, we have exactly that kind of dependency where compiling the mapcar functions compiling the mapcar function requires the invocation of the do macro function, so it must exist. But the do macro function, when it's invoked, invokes the mapcar function. However, things are even more vicious than that, because if we look at the complete example, then you can see here the dependency between mapcar and do. But in order to compile mapcar, we must, of course, execute the define macro. And in order to compile the define macro, we need the def macro macro. Similarly, in order to compile the do macro, we also need def macro. And what we see here down here is another example in part 1 that I showed from ECL. The def macro needs all these macros in order to be compiled. And the way ECL broke up these circular dependencies is that all of these macros here in ECL were written using something other than def macro. That concludes the presentation of this part 2. And in part 3, we're going to cover the following topics. So I want to resolve this circular dependency problem by cross-compiling code on a host Common Lisp implementation. And the cross-compiler will generate bytecodes for the abstract machine. The core is still written in C, and it contains a bytecode loader and a bytecode interpreter. But a lot of code can now be moved from C to Common Lisp for execution on this host Common Lisp implementation. So that summarizes our strategy number 2, which is going to be the main topic of part 3. So I hope to see you when I present part 3. It hasn't been scheduled yet, but I suppose it will be pretty soon.